Your buildings are dead. It is time to make them breathe. This video explores architecture as a thermodynamic system, focusing on form first, then systems, and finally, brute force last. We are facing the mechanical illusion and the broken box. Buildings often lose 40% of their heat. We design sealed boxes that trap heat, then use massive amounts of energy to fix the problem. Passive house design reduces heating energy by 90%, yet is often overlooked.
We need a paradigm inversion. The goal is to design a building that doesn't need an air conditioner, shifting from a sealed box that fights the climate to a breathing habitat that collaborates with it through natural physics.
We can learn from nature, such as the termite mound engine. Airflow depends on the mound's shape and porous walls, creating pressure changes and using sunlight to drive cooling. This passive system uses only dirt, air, and timing, with no moving parts. The Persian Yakhchal demonstrates thermal mass and geometry from 400 BCE. They did not fight the desert, but used its variables to create a thermodynamic machine that produced ice without electricity. The massive walls separate exterior heat from the sunken cold sink. The Japanese Ingawa is an active threshold, acting as a buffer zone. It allows outdoor heat to lose momentum before reaching the core. Wood absorbs and slowly releases humidity, actively regulating the microclimate for adaptive comfort. Fluid dynamics and pressure zones are key. Air flows from high pressure cool to low pressure hot. Positioning a building to block or capture winds creates deliberate pressure zones, using staggered windows to sweep air through the entire space. The stack effect engine leverages the physics of hot air rising and creating a vacuum below. By using small exhaust vents high and large intake openings low, the building automatically inhales cold air, creating continuous convection currents, as proven by the tube house geometry. The thermal mass time lag concept uses earth sheltering and thick masonry to delay heat penetration by 8 to 12 hours. This shifts the interior temperature peak to 10 p.m. when warmth is desired, successfully navigating daily temperature swings without mechanical systems. Evaporative cooling uses state change physics. Water evaporation absorbs massive sensible heat, instantly dropping ambient temperatures. Direct evaporative cooling, such as wet clay tubes or water courtyards, naturally refrigerates interior spaces. The climate-responsive matrix shows that design must adapt to climate. For instance, hot arid requires a boxy envelope and heavy thermal mass, while hot humid needs maximum permeability and ultra-lightweight materials to flush the heat. Biological shading uses deciduous trees as a self-regulating, seasonal system. They provide cooling shade in summer and allow vital winter heat to penetrate when their leaves have dropped. Always specified by biological behavior, not just aesthetics. The modern synthesis, exemplified by PDEC towers, rediscovers ancient physics with modern materials. They capture wind, use microscopic water spray and gravity to pull artificially cooled, dense air into the building's core, proving that true innovation means minimizing machinery. Computational validation allows us to predict physics. Software like TWSIM and Energy Plus models heat transfer through radiation, conduction, and convection simultaneously. This allows architects to manipulate variables like wall thickness and air gaps to guarantee indoor temperatures. We stand at a threshold. The era of brute force architecture is over. We have the computational tools and historical blueprints to design habitats, not sealed boxes. Use geometry as our engine and let the building breathe.